Good morning. May or may not be morning when you're watching. If I seem a little subdued today, it's going to be because I had a rough 24 hours, but mostly because it's pretty hot in this room today. They're doing something with the heating. So hopefully I won't melt. Hopefully we'll get through this. All right, we're going to talk about fisheries. Remember this graph? We're going to see it again. What does that mean? That means fisheries and groundwater have a lot in common. All right, in a minute. Some other stuff. All right, so the first thing to nail down is the communication between the economists and the biologists, right? So, because that's going to tell us what our total costs and in some cases total benefits, especially total benefits, look like. So, here's that graph. All right, so down here we have a little loop in the relationship between fish. It's all backwards. Between fish growth, okay, and the amount of fish that there are, fish stock. And we have this little loop down here that says if the fish get below this level, it could go extinct. Okay, so that's what this little doodad down here is, below the x-axis. All right, so it looks like the Laffer curve, which isn't important if you don't know what that means. It just means that it goes up for a while and comes down for a while, and there's a fish stock that yields a maximum amount of growth, and we call that the maximum sustained yield. And at that point, some people, the non-economists, would say, obvious, maximum sustained yield. That sounds pretty good. Okay, that's what we should shoot for. Unfortunately, they'd be wrong. That's not the most efficient quantity. All right, so let's move forward with that. Okay, so here's a graph that looks like that, but you better be careful because the x and y axis are different. Okay, on the one axis we have total benefits and total costs. And we have fishing effort on the x-axis, and you see it's still that hump shape because if we assume prices are constant, which we will, and we'll assume marginal costs are constant, which yields us that total cost line that goes up it's a straight line. And so, according to, and one other thing to note about the total benefit function is, well, it does look like that biological graph, okay, that one, okay, but it's sort of in reverse. And by that I say sort of in reverse because with this graph, right, the maximum fish stock is out here, okay, out here on the end of the y-x-axis, okay, and with this graph, right, the maximum fish stock is over here, right, at the origin, the 0 point, okay, because as you have more fishing effort, you'll increase fishing effort, you'll have fewer fish, right? Okay, so according to this model, it's kind of a duh model, right? Why is it kind of a duh model? Because the best amount of anything is where total benefit equals total cost. No, you're probably going over here to where the lines intersect. No. The best amount of anything is where the marginal benefit equals the marginal cost, right? Where the total benefit differs from the total cost by as much as possible. And I probably didn't fool you even for a second because I've already stuck a Q star on there, right? That's where the slopes, that's the quantity at which the slopes of the two lines, slope, that's the change in the total benefit, marginal benefit, okay? The slope of the TC line, the total cost line, is constant, okay? So wherever the slope of the total benefit line is equal to the slope of the total cost line, that's a Q star. That maximizes net benefits, right? So that's the most efficient amount. With a slightly larger population, yes, larger population. Remember, it goes from big population to large. Goes from anyway. Here we have a slightly larger population, and if we had the maximum sustained yield, which is still in the middle of the graph, why is that useful? Well, because with more fish, it doesn't cost as much per unit to capture them. Okay, so beyond Q star, yes, we could harvest more fish sustainably than Q star, but beyond that point, the additional cost is more than the additional benefit. Now, you see over here, let me re-emphasize that a little bit more because I did stutter there a few times. Okay, so if we went over to the maximum sustained yield point where the hump-shaped line is at its peak, right, we'd have fewer fish, right? More fishing effort means fewer fish. And so it costs more to capture fish. Okay, so it pays to be a little bit over further here at Q star, okay, where we have more fish, okay, and thus it's easier to capture them. And that's where the change in the benefit is equal to the change in the cost. That maximizes net benefit. All right, so then we have a point over here. I'll let the text mostly fill in the details. Right, and I'm just kind of throwing it out there so we'll have discussion of it. Right, total cost equals total benefit is the equilibrium with open access, which is the state of affairs of many fisheries, especially large ocean fisheries. Okay, as long as there's profit to be made, more fishers will get out there on the ocean and go chasing fish. So until there's no profit left to be made, until the average cost is more than the average revenue or price, more fishers will enter. There'll be more fishing effort made way past the efficient level of fishing effort. Right over here, I didn't mark it on the graph, but right down here, right, that's the fishing effort, a lot of fishing effort. Expensive, lots of boats out there. And just like with the groundwater situation, there are two things going on that speak to the inefficiency of it. Okay, crowding. I mean, literally crowding in many cases because seasons were shortened to try to reduce fishing effort. It just packs in more fishing effort in fewer days, and there's literally a crash derby going on with boats being out there in big numbers in the shorter fish season. And the weather can be bad, other things can happen. They could run into each other, right? So there's a crowding externality. Why was there a crowding externality for the groundwater? Well, because pumps could get too close together. Okay, but in this case, the crowding externality is, well, I guess the fishing boats could get too close together. Okay, and then there's the other thing, the same thing as the groundwater. There's the drawdown externality, where taking more today takes away from having lower costs, more fish to catch in the future. All right, so the maximum sustained yield, that sounds pretty good, doesn't it? Max out sustainability is not the efficient level of fishing effort. Now, if you get into the book, which hopefully you have, and you read the part about the dynamic efficiency, you see that we actually get, in some cases, fairly close to the maximum sustained yield because of discounting. Right? Fish out in the ocean represent money in the bank. Right? So the higher the discount rate is, okay, the more fish will be taken. Right? So this is what's called the static efficiency point, Q star, right here. Okay, the dynamically efficient point is to the right of that, okay, a little closer to the top of the line. If the discount rate's big enough, it'll be right there. Okay, so more fish will be taken now, up to that point, not at the expense of more later, but the extra money in the bank is going to be earning interest. Okay, so okay, so now we're back to the issues of similarities between different things. We've been talking about groundwater. Fisheries is sort of the example that the book uses for all kinds of typically open access resources. And just like groundwater, most critters, animals, plants too, at least initially, are owned by all in common, okay? Common property resource, which in many cases means that it's an open access resource. It's important to understand that a common property resource is not necessarily an open access resource, but typically that is the case, at least initially. And then with management of it later, it can still stay a common property resource, but the management may be such that it is no longer overly accessed, or at least accessed less than it otherwise would be. All right, so migratory wildlife, same thing. Buffalo almost went extinct. So what are the key differences between these resources in terms of management and in terms of the extinction possibility? And even groundwater, extinction is a possibility. If you take too much water out of there, the resource compacts itself, and then it's dead. All right, so in terms of extinction risk, and in terms of management, what matters the most is property rights, okay, and the marginal extraction cost. Now let's just think in terms of the buffalo. Yeah, when buffalo started to get scarce because of excessive, extensive hunting, the marginal extraction cost, kind of a sterile term, extraction, harvest cost, hunting cost, the marginal extraction cost got to be higher and higher. but it's still, but the marginal extraction cost was still not so high that it was economically appropriate from an individual decision maker perspective to not keep hunting buffalo. But for Yellowstone National Park and some private ranches that were big and fenced in some buffalo, might well have gone extinct. Because even when they were getting very scarce, if you didn't shoot it, somebody else would, right? Open access. What everybody owns is treated by each as if nobody owns it. Tragedy of the commons. Okay, so absent appropriate property rights, and what does that mean? Well, that means that either the public through the government is asserting its property right and thus doing things to limit the harvest level to below that which threatens the species, and hopefully to a level at which efficient amount of harvesting occurs. Sorry, my mouth is getting a little dry. All right, so one version of appropriate property rights with the potential for efficiency is if the public asserts its property right, and then either through regulation or a price system, a fee for accessing the resource, can fiddle around with that, assuming imperfect estimation of it. You know, we have our graph. Oops, here it is. We have our graph that says, okay, A, B, okay, this right here, AB is the amount that if the public asserts its property rights and enforces them, that's the level of appropriate fishing fee per unit of fish with command level D1. Okay, so that's one possibility. And then the other possibility is private property rights. Now, not really very meaningful to have, say, that fish out there. Yeah, that one right there, 20 miles offshore and a couple hundred feet deep. It's not very practical to assign property rights to individual fish, but we can assign property rights to a harvest quantity, either a certain amount to catch or a certain amount to deliver to a cannery. Okay, so that's another efficient or a route to efficiency, assuming that the quota, as it's often called, the right to a certain quantity of the sustainable catch, is freely saleable, right? That transfers are easy to make. And just like with groundwater, there often are a lot of restrictions on those transfers to the detriment of efficiency, but on behalf of several objectives, like the fishers don't want to be what are called tenant fishers. They don't want some rich person like a cannery, or even worse, the people that they have to sell their fish to become owners of the fishing rights and thus assign them to the boats on a tenant basis. They don't want that. And then there's that pecuniary externality issue again, which means that if fishing rights move from one fisher to another that may be in a different place, that would impact the use of downstream businesses related to the fish catch and where it's caught. So, as always, conflicting objectives, and of course, efficiency is what we economists can intelligently talk about, and then we can put a price tag through efficiency on those other objectives of, namely, sustaining existing businesses where they are. That's the pecuniary externality issue. Okay, so again, every fishery, every groundwater resource that I've ever heard of makes sense. Starts off with open access, and until the demand increases up to a level that threatens more catch, more extraction than naturally renews, no problem, that's efficient. But that then becomes ingrained in the economic relationships, those pecuniary externality issues. And then suddenly, whoops, with increased demand, from D0 to D1, for example, with increased demand, suddenly that which worked, in some cases for centuries, no longer appropriate. Now we need to quantify the amount that can be caught and not just say, go fish, catch as many fish as you want or you can. Now we have to quantify the total amount. And then the hard part, in terms of getting that system going, sure, we can say, hey, we're catching X fish now, and that's too many given the stock. It may be less than the amount that could be sustainably caught, but because the fish stock was drawn down. It may be it's too much now. All right. So let me pull my graph back up here. I already mentioned the size of the fishing fee per unit of fish at AB. Okay, that amount of dollars per unit, and then Q1 star is the amount of fish that should be caught this time period, given the high level of demand at D1, which will indeed draw down the resource somewhat. And eventually you see my faint line over here again, up here. Yeah, whoops. See, everything's backwards to me, so my hand is on the picture is going opposite direction on what I want it to. Okay, so you see this faint line, the MSC, MPC stuff will increase. And you'll see that on the PowerPoint slides. There's one slide, I think it's slide 4, that has this graph. And then there's slide 5 that has the same graph with another MSC, MPC set of lines that results from drawdown in time period 1. MSC and MPC are increased. At some point, you're going to have a sustainable level unless you reach extinction. Okay? And typically, with open access, the sustainable level is because it's very expensive to fish, and so the amount of fish, a small amount at high cost, is sustainable. All right. At that point, I think I'm going to take a little break to lubricate my vocal cords a little bit, and we'll be back, or I'll be back in a couple minutes, and you can be too. All right, so the first thing to nail down is the communication between the economists and the biologists, right? So, because that's going to tell us what our total costs and in some cases total benefits, especially total benefits, look like. So, here's that graph. All right, so down here we have a little loop in the relationship between fish. It's all backwards. Between fish growth, okay, and the amount of fish that there are. And you see it's still that hump shape because if we assume prices are constant, which we will, and we'll assume marginal costs are constant, which yields us that total cost line that goes up it's a straight line. And so according to, and one other thing to note about the total benefit function is, well, it does look like that, that biological graph, okay, that one, okay, but it's sort of in reverse. And by that, I say non-economists would say, obvious, maximum sustained yield. That's, that sounds pretty good. Okay, that's what we should shoot for. Unfortunately, they'd be wrong. That's not the most efficient quantity. All right, so let's move forward with that. Okay, so here's a graph that looks like that, but you better be careful because the X and Y axis are different. Okay, on the one axis we have total benefits and total costs, and we have fishing effort on the X axis. Good morning. May or may not be morning when you're watching. If I seem a little subdued today, it's going to be because I had a rough 24 hours, but mostly because it's pretty hot in this room today. They're doing something with the heating. So hopefully I won't melt. Hopefully we'll get through this. All right, we're going to talk about fisheries. Remember this graph? We're going to see it again. What does that mean? That means fisheries and groundwater have a lot in common. All right, in a minute. Some other stuff. Fish stock. And we have this little loop down here that says if the fish get below this level, it could go extinct. Okay, so that's what this little doodad down here is, below the x-axis. All right, so it looks like the Laffer curve, which isn't important if you don't know what that means. It just means that it goes up for a while and comes down for a while, and there's a fish stock that yields a maximum amount of growth, and we call that the maximum sustained yield. And at that point, some people,